Alrighty, so in this video, we are going to read this blog from Hacker News, and I just quickly scanned through it. It had the word infinity in it, so that was one of the primary reasons I chose it. So let's just do the usual thing and check out the author. The author doesn't exist. Simon Tatham. Alrighty. Alright. He seems cracked. Oh wow, okay. He created and maintains Putty? Are you serious? Wait, yes, probably that's him. Okay, Simon Tatham is a British computer programmer. He created and maintains Putty, a free software implementation of Secure Shell and Telnet for Microsoft Windows and Unix. Along with an external terminal emulator, he's also the original author of NetWide Assembler and maintains a collection of small computer programs which implement one-player puzzle games. All of them run natively on Nintendo DS, Symbian, S60. I remember when my dad had a Nokia and it was Symbian and he was so proud of it. I was like, yeah, it has Symbian operating system on it. Anyways, Unix, GTK, Android, macOS, and Windows. He attended University of Cambridge and currently works at ARM Holdings. Alright. As I said, cracked. Alrighty. So, The Infinity Machine, an exploration of a fantasy world by Simon Tatham. The Infinity Machine is an extended speculation based on an idea I got from a book I read once. And refined over many years of idle moments, it tries to imagine what the field of computing would be like if computers were able to run infinitely fast. This is not fiction, it has no plot, no characters, and no action. On the other hand, it could almost be called science fiction in the sense that it takes a premise, what if, and explores the consequences. But it isn't science fiction in the usual sense because it tells no story. The Infinite Machine is likely to appeal mostly to computer programs and perhaps also to some mathematicians. It is a speculation at the technical level. It doesn't explore the social consequences of the premise, merely the technical implications for computer architecture, operating system, and compiler design. Networking and cryptography. If you are a hacker type who finds these things inherently interesting, read on. If you are not, you will most likely be bored. You have been warned. I thought this idea up when I was 15 or so. I've been taking this speculation further in spare moments ever since then. It's my own little fantasy world and it's been so much fun exploring it, and I thought I'd write it down in the hope that somebody else might like it too. Dedication. This work is dedicated to Ion Store for writing game, set and math, which contained the inspiration for all of this. Getting started. What might it even mean for a computer to run infinitely fast? In game, Set and Math by Iron Stored, one of the characters make a throwaway remark. Imagine he said, a light switch it on. After a second, switch it off. After another half second, back on again, off after another quarter, one after another eighth, and so on, having the time interval each time. After 2 seconds, any mathematician knows you will have switched the switch an infinite number of times. So after these 2 seconds are up, is the light on or off? Oof. Off, said another character, because you blow the fuse if you switch it that fast. So the first character hit him. The book then briefly mentions that it might be fun to build a computer like that. Well, basically, okay, I'm just gonna explain this really fast if I can. Why 2 seconds? Because basically, sorry about all of this. Just don't look at the rest. Just look at the thing. If you have 1 second, is this pen not working? Pen, please work. Oh, here we go. So these are the wait times, and then you go 1/8 plus 1/16 plus da 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 da. Let's say whatever this equals to is x. Makes sense, right? And then let's just imagine we have 2x. Am I doing this right? Probably. And 2x will be 2 plus 1 plus 1, yes, plus 1/2 plus 1/4 plus dot 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 dot. So now if you have x minus 2x minus x, you have x equals to plus 1 plus 1/2, basically that, and minus 1 plus da 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 da. And as you can see, you can just cancel out everything here with everything here, and then you end up with 2, but you have an infinite series, and that's why you have switched the light bulb, this is a light bulb, on and off for infinite times in only 2 seconds. Back to the block. Okay, so where were we? Oh, okay. The book then briefly mentions that it might be fun to build a computer like that light switch. After the first second, it makes a computation. Oh, we read that. Clearly, such a computer could never exist in this universe, and neither could the infinite memory. It would need to hold the huge numbers. It would need to hold the huge numbers it would be working with. But let's not mere reality stand in our way. Suppose we did live in a world in which it was possible. What would life be like for the programs in that world? Memory layout. The infinity machine's memory, let's suppose, is an infinitely long line of bits, numbered from 0. For every non-negative integer, there exists a bit. How are we to find enough structure in this long line to be able to encompass large numbers of infinitely long strings? The old infinite hotel puzzle, also known as the Hilbert's Hotel, after Hilbert the mathematician, begins to give us the answer. In a hotel containing infinitely many rooms, all of which are full, how do we find room for infinitely many new guests? Simply move every guest to the room with twice the number. Room 1 moves to room 2, room 2 to room 4, 3 to 6, and so on. And then all the odd numbers room are free. So we can split any infinity string of bits into 2 infinite strings by separating the odd bits from the even bits. Each of those strings in turn can be split, and so on. So we can have a binary tree of bit streams, all of which can fit in the machine's memory without interfering with one another. Okay, that sounds promising, but I think with a little more structure, we can do even better. Instead of splitting a string into 2, let's split it into infinite number of substrings. Like this: split the string into 2, then split one, then split one of the remaining strings into 2, then split one of those 2 into 2, and so on. So for a stream S, we have a substream S0 containing all the bits whose indices are 1 mod 2, and substream S1 containing the bits whose indices are 2 mod 4 with indices 4 mod 8, and so on. So any stream of bits can quickly be separated into infinitely many substreams. Better still, the substreams can be separated into substreams, and so on. S2 3, 4, 22, or whatever. The whole system has the property that any substring at any level can be identified by a starting index and an increment and arithmetic progression. And an increment. Okay. Didn't quite get this. We have a substring that containing all the bits and so on. Okay, let's just keep going. There are better properties than that though. S0 contains all the bits whose index within S ends in a 1 when written in binary. S1 contains the bit whose index ends in 10. S2 the bits ending in 100, and in general contains the bit. Oh, I don't think it's 100. It's 100. Contains the bit whose index within S ends in a 1 followed by n zeros. Following on from this, we find that Sijk contains the bits whose index in S ends in 1, I zeros, A1, J zeros, A1, and K zeros. So given an address in the form of start index plus increment, we can easily compute the sequence of substring indices that led to that address from the root stream, the whole memory. In particular, we can move up one level to the stream span and then back down to find its immediate neighbors. This, I think, would be a great basis for the infinity machines memory architecture. Most data types follow naturally from this. An array is easily implemented within a stream by placing element I in Si, and then the array can hold infinitely many elements, and each element is of infinite size and in turn can hold anything it likes. Array elements need not be the same type, so a compiler can map names to array indices, and voila, structure. Okay, and arbitrary. I'm lost. If you don't see me explaining this, it's because I don't get it. So he basically found this system that just like the hotel, just like the Hilbert Hotel. Split into infinite number of substreams like this. Split the stream into two, then split one of the remaining into two, then split substream as contain all the substreams. One mod. Alright, we need to Google 2 mod 4. Excuse me. What does this mean? Oh, please. Not Google. Ah, perfect. Google 2 mod 4. Mod means the remainder when divided by, so 2 divided by 4 is 0 with 2 remaining. Oh, okay. Okay, yes. Okay, fair. Okay. So any system bits can quickly be separated into infinite many substreams. Better still, the substreams can be separated into substreams and so on, S2, 34, 22, or whatever. Okay. So the thing grows exponentially and that's why it's infinite. Sure. An arbitrary integer can be stored in an infinite bit stream in a wide variety of ways, even ways as silly as n zeros followed by 1. It doesn't seem worth choosing one. A pointer has to be encoded as 2 integer, but it must specify a starting index and an increment in order to identify a substring. Because we can always find the parent stream of any substream, we can perform pointer arithmetic by finding S and I such that the pointer P describes Si and then constructing Si plus x for integer x. Interestingly, a pointer physically can't maybe we need to close a few of these. Maybe I'm running out of RAM. Hopefully I'm running out of RAM. Can't even highlight these, so just excuse me for that. Yes. So okay. Because we can always find the parent stream of any substring, we can perform pointer arithmetic by finding S and I such that the pointer P describes Si and then constructing Si plus x for integer x. Interesting, a pointer physically can't run off the bottom of its array. It would be meaningless to try to subtract from a pointer to element 0, and since the array has infinite extent, it can't run off the top either. No more rogue differences blowing things off. Okay. This is a challenging blog. Okay, clocking. My original vision of Infinity Machine was that it would have a basic clock rate, perhaps 1 kHz or something about as feasible, and its basic mode it ticked along at 1 kHz, executing one instruction per cycle. However, one of the possible instructions would be the infinity instruction, the execution of which would cause its 1/10 of second clock cycle to be split into a half, quarter, and eighth, and so on, with one instruction being run in each fragment. So in a single base clock cycle, the machine would execute either a single instruction or a single infinite sequence of them. After an infinite sequence terminated, control would resume at a point specified in the initial infinity instruction. Any bit of memory modified only infinitely, often by the infinite run, would have a well-defined value on exit from the sequence. Any bit modified infinitely often, like Ion Stewart's light switch, would have an unpredictable value. This is modified in the strong sense of having its value change, not in the weak sense of being written to. Repeatedly writing the same value to a bit doesn't count as modification. Alright, this is an interesting architecture from a mathematician's point of view. It forces you to think carefully about what computations can be done in one infinite sequence, or maybe two or three. Computing a Mandelbrot set to arbitrary depth, for example, can be done happily in a single finite sequence. You compute the points you need using increasingly high precision fixed point arithmetic and update the result array repeated. For each point, there will be a precision beyond which the approximations yield the right answer, and so all subsequent computations at higher and higher precision will not alter the value of the pixel. So by the end of your infinite run, the results will have stabilized and will be predictable on routine exit. As a computer scientist, however, I have a slight horror of things which won't nest to arbitrary depth. If this infinity instruction can turn 1 kHz clock cycle into an infinite sequence, why wouldn't it be able to do the same to any finitely long clock cycle, such as the ones inside the original infinite sequence? Then you could have a single base clock cycle divided into infinitely many subcycles, and infinity subset of which could also be divided the same way, so on. Machine could run infinitely many infinite computation within a single tick. Oof. Recreational mathematicians will probably see this as cheating. It makes it much easier to achieve a lot of things which would still have been possible with some contortion on the original restricted machine, but robs us of the pleasure of thinking of the contortions. But the enhanced arbitrarily nested version makes for more interesting computer science, so I'm deliberately choosing to go with that. For the rest of this work, I'll be assuming we have an extended infinity machine. As an aside, here's an example of a very useful operation on the extended machine which I believe is painful on the original. Testing whether an infinite bit stream contains finitely or infinitely many ones. Take one infinite run down the stream. Every time you see a zero, set the corresponding bit in an infinite workspace to 1, and every time you see a 1, set the whole workspace back to 0. The workspace starts as all 0, then every bit of the workspace is modified at most twice and is therefore well defined on exit. Next, set our output variable to infinite and take a second infinite run in which we examine the workspace for ones. If we find 1, we set our output variable to finite. At the end of this second run, we have our answer. Now on the original machine, this requires 2 infinite runs and thus takes 2 base cycles. But the extended machine, it can all be done within another infinite run. Wow. This is exactly why Cambridge and Oxford, they're always topping every other university's computer science department. This is very beautiful to think about, honestly. I like to daydream that one day in my lifetime I can see this. Anyways, instruction set. Speed on the infinity machine isn't much of an issue. Unsurprisingly, it isn't necessary to have a massive array of instructions as long as you have a few which can have the right effects. For example, I speculated that perhaps all you needed was a few simple bit operations and the infinity instruction, and then you'd be able to build addition even of arbitrarily long integers out of an infinity, followed by a long string of bit operations. However, the machine itself must have an inherent ability to do addition at a level below the instruction set, since it must increment its program counter every time it fetches a new instruction. So I think realistically a successor operator must exist in the instruction set. It's quite tempting to use the minimalist register machine instruction set. One instruction increments an integer register by 1, and other branches if it's 0 but otherwise decrements it. Those two instructions together with halt from a machine equivalent to a Turing machine, so with the addition of some IO primitives and the all important infinity instruction, that are sufficient. For personal taste, I prefer to see some elementary bitwise operations and or XOR as well. But of course, you can build an AND using infinity containing adds and subtracts. I'm not going to dwell much farther on the infinity machine's instruction set. There is a wide range of options and I don't think it's very important which is chosen. One thing I would like to see though is for instruction to be infinitely long, a program is an array and the program contains steps along it. This allows load instructions to contain their own literals, and more usefully it allows the infinity instruction to contain its own instruction substream. Alright, interrupt handling. The infinity machine can execute n instructions as easily as 1. The infinity machine can execute interrupt handling. The infinity machine can execute any instruction as easily as 1 in any finite length clock cycle, be it as a base level or some distance down. The machine might choose, instead of executing the instruction in its queue, to execute a notional infinity instruction within which are some number of additional instructions. then the one it was supposed to execute, and then an infinite sequence of NOPs to use up the remains of the subsequence. This provides a natural means by which the machine can handle interrupts. At the beginning of any clock cycle, it checks to see if any interrupts are pending, and if so, it runs a notional infinity which contains the interrupt handlers and the schedule instruction. This achieves an arbitrary amount of processing in response to any interrupt, without affecting the performance of the interrupted code, since the scheduled instruction gets executed at some point during the same cycle. It would otherwise have taken the whole of. This scheme means that the maximum latency of an interrupt is twice the base clock rate. If an interrupt arrives just after the start of a base cycle, which is not an infinity, it will be serviced during a notional infinity in the following base cycle. Of course, if it arrives during the execution of an infinity, the response time might be much quicker. Much quicker. It's worth noting that this interrupt scheme can be handled entirely in software by having the machine emulate itself at full speed. The details are left as an exercise for the reader. Alright, sure, thank you. The obvious was yeah, I don't know, but I'm lost since here. Exactly from here. Trying to imagine the whole scheme of building another infinite stream in this infinite stream and just not ticking. Alright. Operating system. The obvious way to run a multi-process operating system is for the OS in every base cycle to run an infinity in which it lets each process execute instructions until the process reaches a blocking system call. This allows every process to run as fast as its I/O and IPC requirements will allow it. Of course, if the process needs to perform infinite computation rather than just doing finite computations arbitrarily fast, then the process can issue its own infinity instructions within the OSs. The infinity machine requires no hardware memory protection to implement security between processes. Instead of allowing each process to run instructions directly, it would be just as quick to emulate the instructions in the process, and the emulation could provide all the memory protection and security features the OS require. Better still, the emulation could provide additions to the instruction set, and then the machine itself wouldn't have to have a trap instruction for the system calls, or INT, or SWI, or whatever you like to call it. Although the infinity machine removes a lot of the program's traditional worries such as algorithm optimizations, OS design is not one of them. You could emulate each process in a separate virtual memory space which the process couldn't see outside, or you could emulate all processes in a shared memory space and deliberately protect each process from reads and writes by the others. In multiple addresses In the multiple addresses space model, you could provide a system call to set up shared memory between processes. Easily implemented without special hardware. Of course, whenever a process writes to a shared area, the emulator just repeats the write in all other copies of the area. In the single address space model, you can provide a system call whereby a process can allow a part of its memory to be readable to another. There is still more than one way to design an OS, and there's plenty of scope for the usual holy wars about which way is best. More frighteningly still, with the advent of inter-process communication, the time slicing situation becomes more interesting. Suddenly, it doesn't seem to be enough that a process gets one time slice every base cycle. If two processes are communicating, they might want to do serious communication. not just exchanging infinite amounts of data, but exchanging data infinitely often. One time slice per process per cycle only allows a finite frequency of data exchange, and not a high frequency at that. One IPC model that seems peculiarly well suited to this sort of work is the message passing model. Suppose I am in process wishing to communicate with another process. I send in a message as usual. My message is just an infinitely long bit stream, and it processes the message and returns me as a result. My process has effectively yielded a part of its time slices. My process has effectively yielded a part of its time slice to other process. For this to work in the infinity machine, the receiving process would have had to register the address of a message handling function with the OS. The sending of a message is a system call, and when my process executes that system call, the OS responds by running an infinity instruction in which it calls the other process's message handler. The result of the handle is returned to me. The time this takes out of my time slice is predictable. Just one clock cycle, which itself was probably a few infinity sequences deep, so I can pass data to another process arbitrarily often. More confusing still, the other process's message handler might respond by formulating a reply and passing it back to my message handler. So my own process is running again during the part of my time slice I have voluntarily given up to the other process. Indeed, there is no reason why our message handler shouldn't call one another in a bottomless recursion, passing data back and forth, rather like crotons. It may take up infinite stack space, but we have that to spare, and it will all be over in the blink of an eye in any case. This bit makes my head spin, I admit. Well, I'm happy that spins your head too, bro. um, alright. Time slices. More infinity between processes. Well, suppose I'm in process wishing to communicate with another. Okay, yeah, I will probably listen or watch this video one more time myself, just to listen to myself what I've read, and maybe just grasp a little bit of this. Anyways, programming language and compiler design. The obvious extension to a language like C to support the infinity instruction is to introduce a kind of block construct infinity. This will surround the block of code and cause it to be executed within an infinity instruction. For example, this guy. So, this even number is not the sum of two primes. Oh, so printf Goldbach's conjecture is. What is this? Is this the infinitely many 20 primes? INJ I is equal to 2 plus 2. So the number is not the sum of. Ooh. So Goldbach's conjecture is that every number is the addition of two primes. No, wait, what? So, 2, 3 is 5. Okay, so it says while it's bigger than that, we're gonna go. It says if it's not prime, break it already. What? Ah, oh, it breaks from everything. What does it? So 9 is the sum of two primes. 12 sum. 10 is 3 and 7. Yes. What a great thing to choose. What are we doing? Hold back. Conjecture proof. Ow. It was proved. Wow. Um, but why does it say open problem? Alright, so we can solve it with the machine. This fairly simple piece of code would establish once and for all the truth or otherwise of Goldbach's conjecture. The infinite run uses the contents of the braces and at the end of the subdivided clock cycle, execution resumes after the last closing brace. So far, so simple after all. Once we've solved the existence of an infinite machine instruction in the first place, it's hardly difficult to envisage an extra keyword in C to make of it. Although that's not the only extension to C present, notice that those innocent looking integer and integer j must be true integer variables and able to store any whole numbers, no matter how big. Quiet where this lives, long in. Where's the long hole integer? The fun begins when we consider blocking system calls in a program such as read. If our program executes read at the top level, no problem. The call will block the process until data is available and then the execution will resume. But if read is executed within an infinity block, then when the process resumes, it might start another infinity run in the next time slice to finish off the block, since in general a blocking call might be perhaps accidentally executed arbitrarily many infinite levels deep. A compiler for this variant must have some impressive capabilities. Perhaps the compiler would output a small standard interpreter module and translate the program itself into form acceptable to the interpreter. Then the interpreter might be able to have direct knowledge of the process time slices and take care of resuming infinity blocks after a task switch. Alternatively, we could choose to disallow blocking system calls within an infinity block. This isn't horribly desirable either, since catching this at a compile time would require a language attribute on all functions, and worse, on all function pointers, leading to the same chaos when NCC acquired const, as everybody scrambled to update their programs to put the qualifiers in the right places, and inevitably lazy people ended up casting the const away instead of handling it properly. The only remaining solution is to forbid blocking system calls within infinity blocks at the OS level. Have the call return it would block. That's probably the lowest effort solution, but hardly ideal. Okay, so we have networking and cryptography left. Networking in the Infinity Machine has all the problems of IPC without the easy availability of solutions. You have a choice of networking models to consider in the Infinity Machine world. Possibly the most obvious one is the one which allows us to transfer an infinite amount of data in an instance. We'll assume that receiving machine will place the data in a queue and schedule an interrupt, after which the receiving process on the machine will be able to access and use the data. The single biggest question then is this: is it possible for two processes on different infinity machines to exchange data infinitely often? Exchanging infinite amounts of data finally often might not be enough for some applications. In the absence of security requirements, of course, one process could transfer all its data to the other, which could then perform the needed computation and returns the results. But when the two processes don't trust one another, they will each want to keep some data private from the other and will therefore both need to perform parts of whatever computation is taking place. As soon as this computation becomes sufficiently complex, the processes will need to exchange data infinitely often. We could perhaps imagine a situation in which both machines arrange to run an infinity cycle at about the same time, and they exchange data as fast as possible within this cycle. For this to allow an infinite number of data exchanges, though, it is necessary that the infinity cycles end at exactly the same instant. If one cycle ends before the other, then the machine whose cycle ends second will only have managed to execute a finite number of instructions. It's difficult to prove this sort of result mathematically, and if there is one thing the infinity machine will and if there is one thing the infinity machine is, it's mathematically well defined. However, I conjecture that in order for two machines to exchange data an infinite number of times in a finite time span, the two machines must have synchronized clocks. Alright, addendum, as of 23rd of June 2001, interestingly, there is a very useful prediction for two machines exchanging data infinitely many times. It makes for a completely reliable transaction. In finite networking, to perform a transaction between two machines in the sense that either both machines do something or neither does, but never only one, you usually use an exchange of confirmation packets, and each machine completes the transaction if it detects no dropped packets in the exchange. This suffers from the problem that if the last packet in the sequence is dropped, the sending side will not notice. So there's always the chance of one side completing the transaction and the other side not doing so. But with two infinity machines, you could exchange an infinite sequence of confirmations, and each side would complete the transaction if and only if it had received an infinite number of packets. This is perfectly reliable because at most one packet, the initiating one, is ever sent not in response to another. So if I've received an infinite number of packets, I know the other machine must have sent an infinite number of packets. And since all but at most one of those must have been in response to one of my packets, I know the other machine must also have received an infinite number of packets. So with 100% reliability, I complete my end of the transaction if and only if the other machine completes It's cryptography. The infinite machine can bring all known forms of cryptography to a grinding halt, except of course for the one-time pad. Any RSA public key can be instantly inverted to find the corresponding private key, allowing signature forging and decryption. Diffie-Hellman key exchange is no better. The machine can listen to the key exchange, quickly solve the discrete logarithm problem, and update the session key. Hash functions can be received to find other plain text with the same hash. Even symmetric algorithms with a shared secret key are unsafe. Within an appreciable amount of ciphertext and only a vague idea of the nature of the data, ASCII text for example, the machine can try all possible decryption keys and see which potential plaintext fall within the description of the real plaintext. There will probably be few enough left that choosing the right one is a matter of only a moment's thought. One-time pads are still available. Even the infinite machine can get around the fact that trying all best one-time pads is equivalent to trying all possible messages arbitrarily many. What is one-time pads? In cryptography, the one-time pad is an encryption technique that cannot be cracked, but requires the use of a single-use pre-shared key that is larger than or equal to the size of the message being sent. In this sequence, a plaintext is paired with a random secret key, also referred to as a one-time pad. Then each bit or character of the plaintext is encrypted by combining it with the corresponding bit or character from the pad using modular addition. The resulting ciphertext will be impossible to decrypt or break if the following four conditions are met. The key must be at least as long as the plaintext. The key must be truly random. The key must never be reused in whole or in part. The key must be completely secret by communicating parties. Okay. Truly random. No. I don't think. I'm not sure, man. We are fucking with infinity here, so. Alright, I'll take that for the face value for right now. Even though you can get around the fact that trying all possible one-time pads is equivalent to trying all possible messages, arbitrary many other perfectly plausible answers will come up alongside the right one, and there is no way to tell which is which. Oh wow, that's interesting, isn't it? So having brought finite cryptography to its knee, what does the infinite machine offers as an alternative? Before addressing this question, I'd like to digress briefly to talk about random numbers. No finite key of any kind is safe from a listening infinite machine, which can try all finite keys. Therefore, any viable infinite crypto system must require an infinite supply of random numbers. Where to get them from? Perhaps they could be come from the unpredictability of any memory bit modified infinitely often within an infinity cycle. I said in the clocking section that any such bit comes out of the other end of the cycle with an unpredictable value. Possibly a good cryptographic extension to the machine would be to have those bits be truly random rather than merely unreliable. So it's easy to generate an infinite one-time pad. Just execute a simple piece of code. Bit, that's your infinite array of single bits. Infinity, I equals to 0, keeps going, goes to infinity. And then you have integer I, and the integer I grows, and excuse me. Nope. I'm not sure what this is, but probably flips the bits. Sure. And you will have filled your bits are random numbers. Reader exercise. How might a really paranoid OS detect and prohibit the generation and use of random numbers by an unprivileged process? Don't give it infinite access? That's stupid, no? Um, no, I'm not sure. Uh, and you will have filled your whatever, and you have okay, yeah. Assuming a secure channel to transmit this one time, Pat though Alice's future communications with Bob are now assured. She can select infinitely many infinite subsets of this one-time path and never exhaust it. She need only transmit its starting position and step size, just like addressing a substream of the infinity machine's memory, and Bob can pick the same substream out of his copy of the path. Addendum. As of 7 July 2000, oh, this was written in 2001. Good golly. Um, and then this was written. Okay. In fact, given an okay, wow, you really thought about this. That's impressive. In fact, given an infinite one-time key, you cannot merely encrypt unbreakably, but you can both encrypt and make unforgeably in one operation. Break the one-time key into infinite many infinite subsequences into infinite subsequences. Take the first of these sequences and use it to encode the first bit of the plain text. Using 2 bits of key at a time, set one of the first bits of the output chosen by a key bit to be equal to the first bit of plain text XORed with the second key bit. Then set one of the next 2 output bits chosen by a third key bit to be equal to the first plain text bit XORed with the fourth key bit, and so on. So you end up with infinitely many copies of the first plain text bit stored in an unpredictable infinite subsets of the ciphertext XORed with never again used bits of one-time key. Now take the second infinity key sequence and use it to include the second plain text bit infinitely many times in the remaining unused ciphertext bits in the same way. And so the decryptor must check every copy of every bit to provide the MAC, unfortunately. For an attacker to correctly alter even one bit of the plain, they must correctly guess infinite many qubits in order to work out which set of bits must be flipped in the ciphertext. So it is probability zero that this scheme could ever be broken. So that symmetric cryptography sorted, the key must be final, infinite, but once it's there, it's just as safe as a one-time pad and never runs out. Asymmetric cryptography. Then is the hard part. And we are going to require a function that maps an infinite bit sequence, the private key, or some preliminary value that will yield both keys to another infinite bit sequence. The public key non-reversibly for public key cryptography. In fact, we require more properties than that. We will need the transformation to be one which intrinsically also provides a means of using the public key to encrypt something that only the private key can decrypt. But let's consider the general idea of the trapdoor function first. It will provide us with secure hashing if we can manage it, and that's useful in itself. The problem with non-reversibility is the step-by-step analysis. If the output stream contains bits whose value depends on only finally many of the input bits, then it is vulnerable. Knowing the value of that output bit allows you to rule out a lot of values for the input. In general, any input bit which is part of a finite set of bits that determine an output bit is weak. If the input contains weak bits, then there is a problem. Um, um, so a trapdoor function will need to be one in which each output bit depends on an infinite subset of the input bits. I can't think of anything of that kind which would also be bijective, or even close enough to bijectivity to work. Readers are invited to help out here. You know what? I don't promise this, but I gotta message this guy. And probably figure out like the answer to the reader's questions. But anyways, addendum as of 19 August 2006. Some progress on this. Suppose you divide the space of infinite bit strings into equivalence classes such that two strings are equivalent if their bitwise XOR is computable by a finally long program. Suppose you then invoke the axiom of choice. Axiom of choice to find a representative number of each equivalence class. Then, given an input bit string, you XOR it with the representative member for its own equivalence class, giving a computable bit string which you can convert into the final program which generates it and then generate a hash bit by ordinary finite hashing. Repeat infinitely many times with a fresh invocation of the axiom of choice. What is axiom of choice? Okay. In mathematics, the axiom of choice, abbreviated AC or AOC, is an axiom of set theory equivalent to the statement that a Cartesian product of a collection of non-empty sets is non-empty. Okay. Informally put, the axiom of choice says that given any collection of sets, each containing at least one element, it is possible to construct a new set by choosing one element from each set, even if the collection is infinite. Formally, it states that every indexed family of non-empty sets, there exists an index set, such that for every I was formulated by Ernest Zermelo, in order to form a proof of well-ordering theorem. Yes. Well, we read that, but like the blog, I guess takes time to sync. Yeah. Okay. So we're and you have infinitely long bit string derived from your input. I believe even an infinity machine cannot invert this function because taking into account any finite subset of the output bit does not narrow down the possible inputs to the point where they cease to be uncountable. So this looks like a workable hash function. Unfortunately, as far as I can see, each invocation of the AOC requires uncountably many bits to store its output and uncountably many instructions to be executed to invent it, and invented in the first place. So an infinite machine, as I've described it, cannot compute the hash function either. And if you go one better and introduce an uncountable machine, then it can probably invert the function as well as computing it. Does this mean public trapdoor functions are infeasible on the infinite machine, or is there a completely different approach? What do you mean? Uh, Comments to what is that? Anakin at Poblox. Okay, sure. Conclusion. I've presented the infinity machine, a mathematical definition of an infinitely fast computer system. I've explored the effects of infinite storage and infinite speed on operating system design, language design, networking, or cryptography. The infinity machine's world is a radically different one from the one we poor final computer programs live in, and yet hauntingly familiar as well. It still contains unanswered questions, such as whether it would be possible to contrive any scheme of asymmetric cryptography to replace the various finite public key systems that the machine renders obsolete. I hope you've enjoyed my tour of this fantasy world. I'd be fascinated to see any contributions anyone else has. Okay, dude, I'm hooked. Uh, let's see. Simon Tatum. Simon, like just Tatum. Loopy. Mines. Okay, homepage. Welcome to some free software author in Cambridge. About me. Deaths? Changed primary school 3 times, but only went to 3 primary schools due to doing the same one twice. Then Leighton Park reading. Leighton Park reading Hard Knocks. Okay. I also know some number of the users of Monochrome. Played the violin as a child. I gave up when I was 14, 15 because I got tired of the pressure to practice and there were other things I wanted to do with my time. To maintain some interest in things musical though, which is why I created Gunvile. How old is he? 23, starting 40, 23, 24, 47. Is the font symbols for typesetting music clips, note hits, quiver tells, and so on. It's compatible. Oh god, so amazing. Quite impressive in my opinion. But yeah, so I'm not sure how to report bugs if it like crotons. Doesn't it have the infinite machine? Infinity. Free software. A reading which you can download. Okay. Alright, I'm just browsing at this point, so I'm gonna finish this video. But I'm not sure how I can categorize this, but I'll have it in Fantasyland. How about that? Yeah, that's a good playlist for it. Anyways, see you next time.